G'day again. Welcome back to Mathematics 302. Hope you're having a good morning or a good evening, as the case may be. This is Lecture 3 and Part B. Let's get into it. So what I decided for this, having done it and rewritten it, we're going to do open, closed, and infinite sets. That's pretty obvious. We'll do topological spaces. And then I looked at the Hein-Borel theorem and I thought, we really need to do balls in closed and open sets first. So I've moved Hein-Borel theorem to week 7, and we may or may not do it. I'll decide in week 7 about that. So we'll do these three, and that'll be it. Hein-Borel will not be in the upcoming test. Okay, open, closed, and infinite sets. So if a set is not the empty set, then you can identify the lower and upper bounds of the set. So if there's something there, then there must be something lower and something upper in that set. If the set has an upper and lower bound, it is finite. If the set has either no upper or no lower bound, or both, then it is infinite. Now here, identifying what it's saying here is you can identify the lower and upper bound if the bound is not within the set and you can't define that bound, then it's infinite. You can still figure out what it is, but it might not be within the set. We can say, yeah, that's definitely the bound of that set. We can say, well, actually an infinite set. We'll do an example of that shortly. An open set is where where every point has a neighborhood entirely contained within the set. And the next question is, hey, Dr. Everett, what's a neighborhood? So a neighborhood is where you've got a point and a bunch of points around it. Okay. A closed set contains all of its limit points, and this includes where one end is closed and the other end is infinity. So a closed set, let's say you're going from 1 to 2 or 1 to 3. Let's make it 1 to 2. So you've got 1, 2, and 3, and it's closed. So all of those are in there, and 1 and 3 are the limit points. That's fine. If you close a set and leave the other end as infinity, so let's say you go from 1 to infinity, to positive infinity, and usually you'd have a square bracket around the 1 and a round bracket around infinity, then you'd say that's a closed set because it depends on the limit. It only depends on the limit which is closed, not infinity. Now that only accounts for when it's infinity, and not if you've got, like, for example, closed on one side 1, open on the other side 2. That's not the same thing. Okay, that's not closed. An infinite set has an unlimited number of elements and can be either open, closed, or neither. My image is getting in the way. And a clopen set, so here we go, a clopen set, so that's what I was trying to talk about here, is both open and closed. So one end's square, the other end's round, but not round to infinity. And we'll do some examples. Like, I don't know, now. What a great idea. Okay, so here we go. Really easy. Square brackets 0, 1. That is a closed set. It goes from 0 to 1. It includes 0 and 1. It is closed. 0 and 1 open set, round brackets. The 0 and the 1 are not included. So it would start, and we're going to make this number up. It would start at 0.00001 and then go all the way up to 0.999999, etc. But it doesn't include 0 and it does include 1, but that's how the set is defined. This is a clopen set, so it doesn't include 0, but it does include 1. So you can't say it's closed or open, it's clopen. Don't you love that word? There's a new one for you. Put that on Facebook. Hey, I just learned clopen. So here we've got a closed set. So if it's got infinity, like I said, positive or negative infinity at one end, and the other end is closed, then we're declaring that is a closed set. When infinity is included, the definition of a set is dependent on the other endpoint. So this is a closed set. Another example considering the complement of a set. So let's say A is 0, 1, and it's a closed set. So AC, the complement of A, would be minus infinity to not including 0. The union, with the union of not including 1 up to infinity. So this is the union of two open sets. In each respective case, the endpoints 0 and 1 are not included. So A complement is open, therefore A must be closed with endpoints 0 and 1. So this is just really what you're doing with set theory, anything in set theory, is basically just logic. You're just saying, well, if this is true, this can't be true. If this isn't true, then this must be true, that sort of thing. And really, that's all you're doing. It's not very difficult if you're just thinking step by step in terms of logic. That's all we're doing here. B is 0, 1. So this is an open set. So B complement is minus infinity to 0, union with 1, including 1 up to infinity, which is the union of two closed sets. The endpoints of 0 and 1 respectively are both included. So BC, therefore BC, the complement, B complement is closed. So that's a closed set. So therefore B must be open and the endpoints 0 and 1 are not included. Here we go, a little bit of humor. So show that C01 is a clopin set. You could pause the video and do this yourself by considering CC. A little bit of humor. That is not CC. That's a chip. Okay, so C is 0, 1. So not including 0, include 1. So CC is minus infinity to 0, union with 1 to infinity, which is the union of a closed set and an open set. The endpoint 0 is included, the endpoint 1 is not included. So CC is clopin, therefore C must be clopin as well in reverse. So very straightforward logic for you to write out if it said show that something is a clopin or closed or open set. It's very straightforward to do that in terms of the complement. The other way you could show something is closed is instead of using the complement. So the question would say, show using the complement that this is closed or open. It's very, very straightforward. The other version would be show that A12 is closed, and obviously it's telling you by the brackets it's closed, but showing that it's closed, we're going to really say that. For all x in A, x is between 1 and 2 and including 1 and 2. And I've written this out here in words, just in case your brain is not clicking. So for all x, which are elements of A, x ranges from 1 to 2, including the endpoints 1 and 2. So that's just me writing out in words what that is. So now you would write x equals 2 is the upper limit because it's included. So x is included in A. Therefore, sup A is 2. I've put this in brackets. You don't actually have to say this, but handy if you do. X equals 1 is the lower limit, which is obviously clear there. X is included in A. X equals 1 is included in A. And obviously, therefore, inf A equals 1. Therefore, A is closed. So that's a very straightforward argument, really starting with this statement here that tells you what's going on. Show that B equals 0, 1 is open, and same sort of thing. For all x, which are elements of B, we've got x between 0 and 1, but not including which is excluding the endpoints 1 and 0, and again writing it out so in case your brain's not clicking with it. X equals 1 is the upper limit. X equals 1 is not included in B, and again I've written it here, sub B is undefined. X equals 0 is the lower limit, and sub inf B will be undefined as well, and therefore B is open. So very straightforward steps to show that something's open or closed. Proving it, that's a few more steps, and here I've done it with words. So this should help it stick in your brain because hopefully you're pretty good with words. So suppose, and you're going to do it by contradiction. That's pretty much how you do all proofs at this level, is by contradiction. You say, show this is true. Okay, fine. I'll show that it's true by supposing it's not true. So suppose A is closed. Then by definition, the complement AC is open. Suppose we have a limit point of x, a limit point x of A that is outside of A. So here's our supposition of contradiction. We're going to have a limit point of x of A that's outside of A, i.e. x exists in A complement. So you've got like A, and A complement is the rest. So we're going to say this limit point of A exists outside. It's in A complement. So therefore there's a sequence AN in A where AN goes towards X. So if we're looking at a limit point, right? And we've got a bunch of terms in A. Those bunch of terms within A reach some limit, which is x. So AN converges to some limit x within A, right? There's some sequence in A where AN goes to x. It goes towards this and converges towards x, and then it doesn't go anymore. But there exists, and here I'm writing it, that means, or that implies there exists an x in A complement where A complement is an open set. So that means there exists some point x within the set AC, which is an open set. So you've got these two conflicting things. I'm going line, explain where AN goes to x, but now I'm explaining x within AC. So I'm doing two things at once here. Now, we're just looking at, now I'm going to do this line here. So we've got AC is an open set, and x is in AC. All right, so there exists some point x in the open set. Definition of open set, there exists a neighborhood of points. There's a bunch of points which are close to and surrounding any point in the open set. So that means there exists an x plus alpha, with alpha being very, very small, which is in a complement. And also there exists, I should have written an and sign there, but anyway, it doesn't matter, upside down and. There exists an x minus alpha, another very, very small, within AC, and AC is an open set. So you've got these very small things surrounding x within a complement because there's a neighborhood. So you can imagine a dot with a bunch of dots around it. There's a very small neighborhood of points surrounding x because by definition of open set, everything's got a neighborhood because there's no boundaries. So this image in the way up there. This causes a contradiction because the sequence in A which we are saying converges to x can't converge to x. So it can converge to x if we put x right on the boundary, or like it was the next step over from the boundary. But we can't converge to x because it can't get to x. But since the definition of open set says that there exists a neighborhood of points surrounding every point, including x, within that boundary. So it would cross over the boundary. Let's imagine this imaginary boundary. It crosses over the boundary. The next thing it should hit is A, but it doesn't because it's surrounded by a neighborhood of points. Because by definition of an open set, there's a neighborhood of points around every other point. So therefore, it actually can't converge to x. It hits something in that open set. So therefore, that's a contradiction. That can't happen. So therefore, A must contain all its limit points. That limit point x must be inside of A for it to reach that limit. If you've got some sequence and it's going, oh, I've reached my limit, which is the boundary, that boundary must be in A. Okay, so that's typically how you would write it. You might not write it with so many words, but I've tried to write it with enough words so that you can read it and go, okay, I understand what's going on. Hopefully you do. Oh, and there's another person proving that same thing, and he actually does it in reverse as well. So this is going forwards, and then he proves it in reverse. So that's something you might want to watch. Okay, topological space. A topological space is a set X together with a collection of open subsets T that satisfies four conditions. Oops. The empty set is in T. X is in T. The intersection of a finite number of sets in T is also in T. The union of an arbitrary number of sets in T is also in T. Now, alternatively, T may be defined to be a collection of closed sets rather than open sets, in which case the conditions 3 and 4 change. So these two conditions change, and effectively they reverse. The intersection of an arbitrary number of sets of T is also in T, and the union of a finite number of sets in T is also in T. So here you're switching finite and arbitrary. Okay. The very slight difference, but that's the difference when you've got an open versus closed set. in topological space. Okay, and here's some more information about topological space. Let's suppose we've got a topology T on X. So a topology T on X is a collection of subsets of X called open sets, where the empty set and the entire set X are both open. The intersection of a finite open sets is also open. The union of any number of sets is also open. And if T is a topology on X, then the pair XT is called a topological space. Xi may be used to denote a set X endowed with a particular topology T, XT, X with lowercase t. By definition, every topology is a pi system. And you might think, that's great, we're going to have food. Not really, no. They've made up another use for pi, which you would think, how can they make up another use? It's just 3.14. No, they've actually made up a topology called a pi system. Yay for them. So a pi system on a set omega is a collection P of certain subsets of omega where P is non-empty, and if A and B are elements of P, then A intersection B is also an element of P. So that's all, fairly a lot of blurb coming at you, but they've made up this pi system for any set, and we've just called it omega. But it's a collection of subsets of omega where it's non-empty and it's got elements where the intersection is also within P. Better done by examples, I think. Oh, look, let's do some examples. Okay, so these examples are not mathematical examples. These are just examples of where topological space is used in real life. So Euclidean space, when you're doing mathematics in Rn, that's where it's used using an open ball, and we'll get to balls shortly. Metric spaces, spaces where a distance function in metric is defined. Every metric space induces a topology. Manifolds, spaces that locally resemble Euclidean space using geometry and physics. Discrete space and indiscrete space. So they're the typical, image down a bit, they're the typical spaces used in real life. And when I'm talking real life, I'm talking real mathematical life there, not real life external to maths, where they're using topological space to solve problems or to do some sort of thesis. Okay, question 1, and this is back to more reality of things you might like. Okay, let X be A, B, C, D, E, F, and the collection T on X given by T equals X, empty set, so X is the whole lot, empty set, A, F, AF, ACF, and B, C, D, E, F. Find the closed subset of X and find the clopin subset of X. So you might want to pause the video and see if you can think through what the answers are. And here we go. So what you're going to do is find the complements of all the open sets to determine the closed sets, then identify which sets are present in both the open and closed collections to find the clopin sets. That's what you would do. In reality, this is actually quite simple for this question. The closed subsets of X are all of them. Okay, they're all closed subsets of X. Now, here's the trick. The clopin subsets of X are the empty sets and all of X. So the closed subsets of X are the empty set X, A, and all the other combinations. The clopin subsets of X are empty set and X. And you think, how can it be there and there? Well, what's a clopin subset? It's a set which is open and closed. So that's included in both. And that leads me to the next question, and this is a pretty good one. I really like this question. Is the empty set open or closed? So have a think about that. Is the empty set open or closed? And the answer is, it's both. If a set has no elements, and here's the logic, and I really, really like this logic. This is really good. If a set has no elements, then it's called an empty set, right? There's nothing in it. As there are no points in an empty set, it does not contain any of the boundary points. So by definition, it's an open set. Also, since there are no points on the boundary, it includes all its boundary points, so it's closed. So I really like that definition. It really makes you think, you can pose it there. If you could think of another question like that for your high school students where you've got some answer which is both, I really like that sort of logic that sort of stretches your brain. Balls. The last thing I want to do is balls in closed and open sets. And this is the reason I didn't want to go on to that theorem because if you haven't done balls in closed and open sets, you've got no idea how to deal with the Hein-Borel theorem. So a ball is a set of points at a fixed radius around a point. So a ball is a specific type of neighborhood. So a neighborhood is a bunch of points surrounding a point. And you've got your bunch there, that's your neighborhood. So a ball is a specific type of neighborhood. And I thought the best way to describe this was with images because they'll stick in your mind. And I might shrink my picture and make myself way up here. There we go. Okay, so here's a closed set. And notice it's got a fixed firm boundary. And here's an open set. And it's got a dot, 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 dot. Because it goes on, it literally goes on forever up to, to nowhere because it doesn't have an end. So here I've got a point in a closed set. And I'm going to surround the point with other points. Okay, so there's a set of points of a fixed radius surrounding a point. So it's got a neighborhood. So this point has a neighborhood. Yay. Now I'm going to put a point on the boundary. If I put points in there, I can't surround it. So there's not what we call a neighborhood around that boundary point because it isn't surrounded by points. And we do the same in an open set. Here we go. Here's a point. Surround it with points and yay. Oops, go back one. So that point has a neighborhood. So now I'm going to find the boundary point and look at that. It's outside the open set. And I can put a neighborhood around that and go, yep, that's got a neighborhood around it, but it's outside of the open set. The boundary is outside. So a set is closed if and only if there's that double F, it contains its boundary points. And a set is open if and only if it does not contain its boundary points. And great example is really just square brackets, round brackets. 1 and 3, 1 and 3, 1, 2, and 3 are all contained with 1 and 3 being the boundary points. So this could be, for example, this could be 3 as a boundary point. This could be 2 and 1 could be, I don't know, over here or something. So you've got 1 there, 2 there, and 3 there. This is just making it very, very simple. And here, using the same numbers, 1 and 3, so this would be 3, this might be 2, and 1 would be out here. So the boundary point is actually outside. It contains everything else all the way up to, but not including 3. But the boundary point is outside the open set. Okay, so hopefully that helps your understanding to keep some images in your head for what balls are and also the boundary points. Okay, that's it. That's all I've got for you for this week. I've left a few questions for you to do. God bless you. Stay safe. And I'll see you next time. Okay, bye.